Good afternoon, everybody. In this seminar, I want to overview some research topics and plans that we are currently performing and we will perform next year. So this is the content. I will introduce in total 4 major research topics that either we are performing or we will be performing starting from next year. So first, I have to introduce why we have set this kind of plans. And first, we have to know that there are flourishing activities on advanced reactor system development across the world. Major nuclear powers like the United States, China, and Russia are expecting continued role of nuclear energy in the future, and therefore they are seeking for ways to make nuclear energy more deployable. So they are trying to escape from the limit of conventional large power plants that are located in remote places, and they are actively developing multi-purpose small modular reactors. They can replace existing coal plants and they can provide heat for producing hydrogen, or they can be deployed to some undeveloped remote places and provide energy. So while the LWR type SMRs like the NuScale one can be analyzed with conventional codes, there are also many advanced reactor concepts that require completely new approaches. For example, heat pipe cooled microreactors, pebble bed reactors, and molten salt reactors. So based on this fact, we want to begin some new research projects on advanced reactor analysis. The second thing we have to notice is that there are also flourishing activities on multi-way, multiscale, multiphysics analysis. Now, until recently, our interest on the multiphysics analysis did not go above two-way coupling, which are neutronics and sub-channel thermohydraulics. However, many research groups across the world have already been pursuing multi-way, multiscale coupling in recent years. For example, the most representative one made by Kessel, which is Vera, is almost 5-way coupled in reactor scale and system scale. And also INL is developing a lot of multiphysics applications based on MOOS, including ULab 7. And also Carey has been developing a coupling system which integrates master, Cupid, reactor vessel version, and Mars. Also KNF is developing a safety analysis system that couples neutronics, thermohydraulics, fuel performance, and the system code space. Finally, the KHMP guys are working together with UNIST guys to couple their neutronics code RASK with sub-channel codes, fuel performance codes, for crowd analysis codes. So based on this kind of activities, we have to stay competitive with other groups by retaining such tools on our own and exploiting our strength in high-performance computing. So we should not be limited to neutronics and thermohydraulics coupling, and we have to extend our scope to fuel performance and system analysis and others. So what we have to pursue in future researches is that we first have to develop the analysis codes whose application is not limited to regular PWRs. And we have to pursue a lot of co-work with other groups in multiphysics research. It would be the best if we can do everything on our own, but practically we cannot be experts in every field. So we must create a cooperative environment which we can work in with people from other fields. So based on these messages, we are performing In fact, this project is already ongoing, but the first project that I'd like to introduce to review is the analysis of heat pipe cooled microreactors. The heat pipe cooled microreactor has a lot of non-conventional design features compared to the PWRs. First, it's a fast neutron system because there's no moderating material. And the heat is removed passively in the heat pipe reactors using the liquid metal heat pipes. And in contrast to the liquid water reflector in the PWRs, the reflector in the heat pipe reactor consists of a metal monolith, and all the fuel rods and heat pipes are inserted into the monolith. And the reactivity control is done by rotating control drums instead of vertically moving control rods. So in order to analyze all these kind of non-conventional features, we have to extend our code capabilities accordingly. So we have been performing projects with Professor Cho's lab for the last 2 years, and we have achieved quite a lot of progresses. Starting from the extension of program capabilities to the unstructured mesh treatment and for fast reactor system analysis, we recently achieved coupling with open form, and very recently, Im Jae-ok had made a system to automate the CAD modeling so that we can generate more bigger CAD models more efficiently. So that's what we have done so far and what we have to pursue after this moment is we have to implement the Monte Carlo transient feature in Pragma. It's obvious that transient simulation is essential in the analysis of heat pipe reactors in order to demonstrate its self-regulating capability. Because it's a passive system, it has a self-regulation feature, which is achieved by the reactivity feedback caused by the thermal expansion of monoliths. However, performing transient analysis with Monte Carlo method is extremely challenging in the computational aspect because the time scale of neutrons and delayed precursors are very orders of magnitude different. But a few Monte Carlo codes have succeeded in demonstrating transient simulation capabilities, although in very limited scale. For example, SNURPL had achieved coupling with open form in transient mode, and it could simulate the Godiva prompt critical burst simulation. And Guardian, developed by the Hungary Budapest University, demonstrated a GPU-based Monte Carlo transient simulation. And they could analyze their training reactor transient situation using their code. So it means that the Monte Carlo transient calculation is technically possible. So we have to implement a state-of-the-art transient solver in our Pragma code as well, referring to the preceding works. And another challenging task is the mesh deformation simulation. As mentioned, one of the major reactivity feedback mechanisms in heat pipe reactors is the thermal deformation of monolith reflector. So mesh deformation capability is essential to properly model the reactivity feedback by thermal deformation. The current coupling is made simply by changing the density while keeping the meshes. But cannot correctly reflect the feedback effect because it doesn't preserve. 지금 인터넷 연결이 불안정하다고 해서
지금은 괜찮아.
네. So the current feedback algorithm is to simply change the density while keeping the meshes, but it cannot correctly reflect the feedback effect because it does not preserve total mass. However, the mesh deformation introduces numerous technical issues to consider in actual simulation. It's not as easy as it is thought. The biggest issue is that we have to confirm this first, but our concern is that will the cells be preserved by open form? If the number of cells changes by collapsing more than 2 cells, or if that kind of things happen, the mesh deformation simulation will not be even possible because there's no way to change the number of cells during Monte Carlo simulation. It has to involve changes in the tally data that has been accumulated throughout the cycle, which is not possible, I think. So the biggest assumption should be that there's no change in the number of cells and the mesh deformation should be modeled by only changing the position of the points. If that can be done, the next issue would be how to minimize the cost of repeated geometry update. And the other two technical issues only occur in steady state calculation. But but these technical issues are quite significant. First, because the geometry is continuously changing, we have to know the way how to determine the average deformation after finishing the active cycles. Because what the geometry that we see after finishing the active cycles is just the geometry of a single state point, not the average of the active cycles. So how to determine the average deformation is an issue. In transient, it's okay because in transient, each step is just a state point that we are passing through time. But in steady state, it's not. And the second issue would be that does the fission source have to be converged after each geometry update? If the geometry changes, the fission source will change somehow. So do we have to reserve some inactive cycles after geometry update in order to do tallies? So all these kind of technical issues should be resolved prior to implementing the mesh deformation capability. And so I think this task will be the most challenging part in this project. So the personnel in charge for this project is Im Jae-ho, as you all know. He will take over the main developer of Pragma after I leave, and he will mainly working on improving the general geometry treatment capability of Pragma, along with some maintenance jobs required by KHMP. So the remaining task in the project consists as follows, and we are currently at this position. So we are expecting 3 years for the completion of all these tasks. But the development of plan for the mesh deformation capability is subject to the progress of the Thermohydraulics Lab, because they have not yet figured out how to perform actual mesh deformation in open form. But other plans are just our standalone tasks, and we can proceed with our own plan. So this is the roadmap that I think that Im Jae-ho has to follow. The last task will be the depletion simulation, but this is in fact not the scope of the official project, so it's our own objective. The second project the second project topic is the analysis of pebble bed reactors. The TRACER fuel used in the pebble bed reactors I think it's politically correct fuel that cannot melt. The world is increasingly emphasizing the nuclear safety and also nuclear non-proliferation. And TRACER fuels can achieve both due to its robust nature. So in this regard, reactors of pebble bed and prismatic design, which loads the TRACER particles in some regular format, are being actively developed, which introduces various challenges in simulation aspect. So the second project would be to tackle these simulation issues with our programmer code. So this plan will focus on the analysis of pebble bed reactors, mainly pebble bed reactors, but extension to the prismatic designs will be pursued. In order to analyze pebble bed reactors, we have to first develop a dedicated tracking module. Program has already the capability to simulate unstructured meshes with built-in triangle intersection program, but it will not be used in pebble bed reactor analysis, and special optics intersection program for sphere primitive will be developed. Because representing a single sphere with polyhedral meshes is extremely inefficient. So this sphere will be modeled as a single primitive instead of using some like tetrahedrons. And the modeling of pebbles will not be performed by a CAD software, but they will be treated as a special geometry object. Because pebbles are so-called active objects, they have to expand, shrink, and roll around continuously. So they will never be a fixed geometry, and it requires special treatment. So the pebble geometries will be overlaid on the original unstructured mesh geometry. The core itself will be modeled using a CAD software, and the pebbles will be filled in some designated zones. So this will make the overall geometry treatment complex, and devising ways to implement it in a fancy way is ongoing. And because the pebble bed reactor has extreme double heterogeneity due to the existence of TRACER particles, considering intersections with every TRACER particle and its coating layers is not practical. So we will give each pebble the same distribution of TRACERs. So we are not going to generate the TRACER distributions for every pebble, but we will use the same TRACER distribution for all the pebbles. But we will give the rotations to each pebble so that almost fully random TRACER particle distributions can be modeled through simple rotational transformation of neutron coordinates. And the standard tracking, geometry tracking is performed between pebbles, namely the intersections will be calculated at the surface of the pebbles, but the delta tracking scheme will be employed inside each pebble because it's too inefficient to calculate the intersection of every TRACER particles. So during the delta tracking, if a collision occurs, the TRACER particles will be located efficiently at each collision by some kind of grid cell search schemes. So if a collision occurs at a certain grid, we will look for the TRACER particles that are contained in this grid and determine whether we have collided into a TRACER particle or not. So we have this kind of strategies for the tracking module. And also we have to consider how we will achieve multiphysics simulation. And I'm considering coupling with the Sophia code for the multiphysics analysis of pebble bed reactors. the granular behavior of pebbles is almost impossible to model explicitly with conventional mesh-based multiphysics calculation tools, which is also known as Eulerian-based approach. But smoothed particle hydrodynamics, which is a mesh-free Lagrangian approach, significantly simplifies the model implementation of such problems. The SPH method is typically applied to this kind of problems that has very complicated boundary conditions or some kind of free surface problems. And because the SPH method handles particles explicitly, I thought it is the most suitable way of enabling multiphysics simulation in Pebble bed reactors. And we have the code named Sophia in our department, which is a high performance SPH code. And so I think it's a strong candidate of the multiphysics tool for the PBR analysis. So I expect the Sophia code to provide the physics-based packing of pebbles by gravity and friction. The initial distribution of pebbles cannot be just set randomly. It should consider gravity and friction, and that can be done by the Sophia code. And also I expect that it can produce physics-based relocation of pebbles by thermal expansion, pebble flow, and refueling. So the pebble bed reactor is not at steady condition. It always moves the internal pebbles, and also as the pebbles get heated, it will expand and change its distribution. So that kind of phenomenon should be modeled as well, and I think Sophia can model that kind of phenomenon. And it will be able to simulate the heat transfer between pebbles, and it will determine the pebble temperatures. Also, the helium flow through this porous media can be simulated using Sophia. So I already finished talking with Professor Kim Eung-soo about my idea, and if we can settle a project on this, we will be able to perform a joint research. And because Pebble bed reactor is has a very long cycle length. Actually, it has no concept of cycle. It's continuously operating. We have to develop a method for cycle analysis. First of all, for the depletion calculation, we will perform pebble-wise depletion because depleting each tracer particle is not feasible at all. But continuous refueling of pebbles makes cycle analysis of PBRs non-trivial. So I personally don't have much knowledge about how the candle reactors are designed, but I think there are similarities between the continuous refueling of PBRs and candle reactors. So I think we can refer to the design methodology of candle reactors to develop the cycle analysis methods for Pebble bed reactors. So this task will be Kwon Sung-jun and Im Jae-wook will be responsible for this task. Kwon Sung-jun is taking the lead of the overall development, and Im Jae-wook will assist Kwon Sung-jun with his knowledge of the Pragma code itself and his early experiences in the development of optics primitive-based geometry module in Pragma. So we are currently developing a tracking module dedicated for pebbles, and because there are still some time to begin a joint research with the Professor Kim Eung-soo's lab, we'll first demonstrate our standalone calculation performance and then demonstrate Sophia coupled core simulation. Then we will try to reflect the pebble relocation and develop cycle analysis method. I'm also expecting 3 years for this for all the tasks to be completed. But because the development of plan of the Sophia site is yet unknown, so this Sophia coupling plan will be subject to their plan. The third task we are planning to perform is to develop a code that will inherit nTRACER. The nTRACER code was first launched in 2009, and it has been more than a decade of development period. But due to that long development period, it became quite unsustainable. First of all, the stability is only conditional in nTRACER. The solution scheme always risks divergence, even though 1D solver is not perfect. So because of this instability, users are forced to spend a lot of time in tuning the inputs and rerunning the calculations by tuning the options until reaching convergence. So considering all the time spent to reach convergence, trial and errors, but I think the advantage in calculation speed is quite diminished. And the second limitation that makes nTRACER unsustainable is its limited applicability. I think Sungwook will most agree with this. The cross-section library generation procedure is overly complex and difficult to maintain. I heard that there are almost 10 codes that has to be used to produce the nTRACER library, and this is too complex. And also the cross-section library has to be regenerated for different types of cores. Also the geometry module is not very flexible and it's difficult to extend. The third limitation is more related to practical reasons, but it's that the code is too much sprawled. The code development process is rather haphazard. Because it was developed by so many people, currently nobody has the knowledge of the global structure of the code, and it is very difficult to keep all parts of the code comparable. So if a person develops one feature, the other feature breaks down, and the main developer has to suffer on debugging. And there exists more than 170,000 lines of source code, but many of them are either the vestiges of temporary implementations and non-functional lines and obsolete features. So all the 170,000 lines are not necessary. It can be much shorter than today's nTRACER code. And the last issue that is not currently very limiting, but it is expected to limit in the future is its legacy programming by Fortran. The support for Fortran is diminishing due to the decline in user community, and it is becoming increasingly difficult to utilize external libraries and modern programming features with Fortran. For example, the CUDA standard support for Fortran is more than a year late than C++, so you cannot deploy the newest features when necessary. So in the new code, we are pursuing a completely different approach of cross-section treatment. We are currently devising ways to reformulate the neutron transport problem with respect to the moments whose basis functions are obtained from an orthogonal decomposition of a set of continuous energy flux spectra. So if this is successful, if the transport equation can be solved with respect to the moments of continuous energy flux, it will significantly simplify the library generation procedure. And a single library will be applicable to different types of reactors with properly generated basis functions. And also, if this method goes successful, we expect to achieve continuous energy accuracy with multi-group codes. And the transport solver will also become more robust than the current one. We are trying to implement a transport solution scheme so-called planar MOC embedded orthogonal mesh SN, suggested by Young in MSc 2007. So basically, it retains the computational advantage of using planar MOC, but the axial solution is resolved by relatively cheap but fully 3D transport, which is the corrected diamond difference SN on pin homogenized mesh, which is parallelizable on GPU. The standard SN method is not easily parallelizable on GPU because it has some sequential nature caused by the band sweeping, but the diamond difference SN is fully parallelizable, similar to FDM. And that diamond difference correlation will be modified using the planar MOC solution. So by doing this, we can evict transverse leakages in the axial solution, which will make the solution scheme more robust. Also, in the new code, some significantly enhanced flexibility will be provided for cell modeling. So this project is being led by Lee Han-gyu and Kim Kyung-min. Lee Han-gyu will focus on the development of innovative cross-section treatment methods. And Kim Kyung-min will develop flexible geometry module and high-performance, robust transfer solver. So we are currently at the beginning phase. And I expect 2 years for the completion of this project. Currently, we are not yet considering depletion or thermal hydraulic feedbacks. In 2 years, we just want to establish a stable Neutronics solution scheme, and considering depletion will be a further task. The last project that we are planning to do is multiscale multiphysics safety analysis. As you may know, I'm currently developing IRIS multiphysics code coupling framework, which is being developed to serve as a coupling hub of the SNURPL code system for PWR analysis. I'm making this framework to overcome the limitation of conventional coupling schemes and to realize what I call all-to-all coupling by providing common environment and a driver routine on which multiple codes can be connected with each other. And IRIS was intended for enabling multi-physics calculations in multi-way. I mean, it was intended to couple fuel performance and other physics in reactor scale, but I did not consider multi-scale like system code. But we recently set a new initiative to establish a multi-way, multi-scale, multi-physics safety analysis system using Vanguard and IRIS. So I extended the plan for IRIS development to include system code. So in this extended plan, I will going to couple system analysis codes running on desktops such as Mars or Relab with the IRIS main module running on servers through the TCP/IP sockets. And Vanguard will have transient capability in the near future. Vanguard has demonstrated its capability as a comparative nuclear design tool. We have performed several VNVs by performing cycle depletion calculation of multiple commercial cores, including APR 1400, AP 1000, and Pebbles, and comparing them with whole core transfer solutions. And Vanguard renders unmatched performance over its pinwise nodal competitors, which are Scope 2, DIN3D, and Bamboo version 2. So now that we have a capability for efficient nuclear design, Vanguard is now being extended to transient mode for safety analysis, in which the strength of Vanguard in terms of performance will be maximized. So Vanguard is expected to finalize our research on pinwise two-step transient and become a production-grade transient simulator. So in fact, we have a number of earlier researches related with penalized transient simulation in our lab, which was Finkus and the work by Hwang Jun-taek. But the research with Finkus was very much limited to small-scale mock-up problems due to its lack of capability to solve large problems. And in case of Hwang Jun-taek's code, the performance itself was fairly efficient, but it could not handle group constants. In fact, before we optimized the group constant generation procedure for Vanguard, the penalized group constant generation system of nTRACER was extremely inefficient, which fundamentally hindered the establishment of a proper penalized two-step code system. But now that we have Vanguard and an efficient penalized two-step group constant generation system, I think we can achieve what we have aimed in the beginning of Finkus project. And moreover, it was revealed by Hong Yan-sik that penalized FDM has very large discretization error hidden under the error cancellation. So the preceding researches based on FDM have become less meaningful today. But because Vanguard is a nodal code, it is free from that kind of problems. So as a final picture, we are trying to establish iris-based Vanguard multiphysics multiscale accident analysis. Vanguard transient solver will be coupled with transient sub-channel field performance and system solvers using the iris framework. So we will have a strong multiphysics, multiscale, multi-way multiphysics tool on our hand. So the development roadmap for this project goes as follows. Jeon So-yoon is the primary developer of this plan, and Kwon Sung-jun will work jointly with the Fuel Lab for coupling the gift code on iris. I expect 9 months for this development, but the gift development by the Fuel Lab is continuously delayed. So if we cannot expect the gift development to be done rapidly, we will proceed without the gift code. So I have introduced a number of projects that we are performing and planning to do. And I think if all these projects can be accomplished successfully, we will have a lot of achievements.